All right, in this chapter we will consider systems that possibly have many degrees of freedom, but we will look at the dynamics of the system close to its equilibrium state. So let us write this down. So we have a system with many degrees of freedom, possibly many degrees of freedom. So let's say we have f degrees of freedom, and we have a Lagrangian L, which is the difference of kinetic energy minus potential energy, and we want to assume that the kinetic energy, as is often the case, has the quadratic form 1/2 sum ij going from 1 to f. Then we have some matrix element mij, which may depend on the coordinates but not on the velocities, and also not explicitly on time. Qi dot Qj dot. We had considered earlier how you arrive at this quadratic form if you start with Cartesian coordinates, where the kinetic energy has this form, sum over all components, 1/2 mass times velocity squared, and then you perform an arbitrary coordinate transformation, time-independent coordinate transformation. Then in the new coordinates, the kinetic energy will generally have this quadratic form with sort of no longer a scalar mass, but sort of a kind of mass matrix whose entries may depend on configuration, but not on velocity and not on time. And for the potential, we are assuming that the potential U depends only on the configuration, but it does not depend explicitly on time, and it also does not depend on velocities. We had discussed earlier in the general part of this lecture that in this case, when the kinetic energy has this quadratic form, and when the potential is independent of time and velocities, then first of all the Hamilton function equals the physical energy, and this physical energy is conserved. So under these conditions, we have energy conservation. Now the system, we assume, has some equilibrium configuration, and we say that the equilibrium configuration is at some Qi naught. So these are the coordinates. That's the configuration of the equilibrium. When the system is in this equilibrium, then the momenta vanish, and so then this configuration is constant in time. And we are interested in the dynamics of the system close to this equilibrium configuration. So you can think of, say, a system of many masses, and these masses are all connected with each other by elastic springs, for example. And there's some equilibrium configuration in which these masses don't move, and now you tip against one of these masses, and this mass starts to oscillate, and it will these oscillations will propagate, so the other masses will also start to oscillate, and the whole system will start to move and have some dynamics close to equilibrium state. So let me write this down. We are interested, we consider the dynamics close to this equilibrium. So we are assuming that the QIs are close to, approximately equal to their equilibrium values. This assumption that we stay close to the equilibrium justifies an approximation, both for the kinetic energy and for the potential energy, and hence for the entire Lagrangian. And that is the so-called quadratic approximation. Let us first consider the quadratic approximation for the potential. The basic idea here is that we do a Taylor expansion of the potential around the equilibrium configuration. So we look at the potential as a function of configuration Q. We say Q is close to the equilibrium configuration, and when we Taylor expand around this equilibrium configuration, we have the lowest order term here, then we have a linear term. I introduce here in this next to this partial derivative an index 0, which is supposed to mean that we consider the partial derivative at the equilibrium configuration. So we have to multiply this partial with respect to with Q minus Q naught. And then we have a second order term, sum over ij. Then we get the matrix of second order partial derivatives of the potential with respect to Qi and Qj, again evaluated at the equilibrium configuration. And then we have Qi minus Qi naught and Qj minus Qj naught. And then we have higher order terms in the deviation of the configuration from the equilibrium configuration. The zero order term, the potential evaluated at the equilibrium configuration, that is some number, that's some constant. It no longer depends on Q. It's just a constant value. And therefore it will not have any impact on the dynamics of the system. It just shifts the energy by some constant. It shifts the energy scale, and that doesn't have any impact on the dynamics. So we can neglect this term. We can say, well, this is a constant, and this is irrelevant for the dynamics of the system. The next order term is the linear term. In there feature these partial derivatives, partial of u with respect to Qi. These give rise to forces, generalized forces in the system. But in equilibrium, all these forces vanish. The quadratic term, this is the lowest order term that really gives non-trivial dynamics near equilibrium. So this is the lowest order term that yields interesting dynamics near equilibrium. And now, since we want to restrict ourselves to the dynamics near equilibrium, we will focus on that second order term. We will neglect all higher order terms, and we will focus on this quadratic term, which is the lowest order term that gives an interesting dynamics in the neighborhood of equilibrium. The form of this second order term in the Taylor expansion suggests that we introduce new coordinates, namely the deviation of the configuration from the equilibrium configuration. I denote that by little xi, but I should warn you that these are not Cartesian. In the past, I had reserved the coordinates xi for Cartesian coordinates. Here I use xi to denote the deviation from equilibrium, but since the qi's can be arbitrary curvilinear coordinates, the distance xi is not necessarily a Cartesian coordinate. Now, in terms of these new coordinates xi, and in the quadratic approximation, so we drop all terms of order x cubed and higher, the potential acquires a very simple form. It's 1/2 sum over ij, and then I introduce a coefficient matrix Vij, whose components are defined as the second order partial derivatives of the potential with respect to qi and qj at the equilibrium configuration times xi xj. So this formula here is a very simple expression for the potential in the quadratic approximation near the equilibrium configuration. Then let's turn to the kinetic energy and finally to the entire Lagrange function. Remember, we assumed that the kinetic energy has the form sum over ij, then some coefficient mij, which may depend on configuration. And then we have qi dot qj dot. Well, we can immediately replace qi dot by xi dot and qj dot by xj dot, because they differ only by the equilibrium configuration, which doesn't change in time, so the time derivatives are identical. Now, if we want to be consistent and stick to second order, at most second order in the axis, in the sort of the x coordinates, then here we already have second order. We have xi dot and xj dot. That's already second order in x, second order in the deviation from equilibrium. This implies, and we don't want to go to higher order. If we look at this coefficient matrix Mij, which is a function of q, we could again Taylor expand that around the equilibrium configuration. We could write that as Mij at the equilibrium configuration plus, and then so linear term, quadratic term, and so on, which would be first order in x, second order in x, and so on. But since in total we don't want to be higher than second order, we carry in fact only the zeroth order term, and we replace q by the equilibrium configuration. So this is in the quadratic approximation, we don't want to include any corrections to Mij at the equilibrium configuration. So without any further calculation, we immediately find the approximate result in the quadratic approximation for the kinetic energy. It's sum over Ij, and then we have a coefficient matrix which I would like to call Tij, and which is nothing but the coefficient Mij evaluated at the equilibrium configuration times xi dot xj dot. So what we have achieved is that now we have both the potential and the kinetic energy to second order in the x and the x dot. This allows us to express the Lagrange function in terms of x and x dot in this quadratic approximation, that is 1/2 sum over Ij, and then we have first the kinetic term, which is Tij xi dot xj dot, minus the potential term, which is Vij xi xj. And we can write that in a compact notation as a scalar product. We can say the kinetic energy, that's the scalar product of the vector x dot with the matrix T acting on x dot, and the potential energy we can write as a scalar product of the vector x with matrix V acting on vector x. So T and V are now the matrices whose coefficients are given above and whose coefficients are constant. They are evaluated at the equilibrium configuration and they don't depend on the x's or the x dots. What can we say sort of generally about these matrices T and V? First of all, both matrices are symmetric. Well, for V this is obvious because it's the matrix of second order partial derivatives of the potential with respect to the q's, and you can exchange the order of partial derivatives, so this matrix V is symmetric. As for the matrix T, this is something that we had discussed earlier when we considered sort of transformations from Cartesian coordinates to arbitrary generalized coordinates, time-independent transformations. Then we had obtained this matrix Mij, and we had shown earlier that this matrix is symmetric, and therefore also the T is symmetric. What else can we say? We know the kinetic energy is always positive. So whatever x dot, when it's different from 0, the kinetic energy is positive. Whenever we have motion in the system, the kinetic energy is greater than 0. This implies, now since the kinetic energy can be written as the scalar product as above, and if it must be positive for any choice of x dot, of the vector x dot, that is different from 0. This implies, by definition, that the matrix T must be a positive matrix. And then finally, there's a similar statement that we can make about the matrix V. with an important assumption, however, that we need. If we assume that the equilibrium is stable, then the potential must have a genuine minimum at the equilibrium configuration. And then the matrix of second order partial derivatives must be strictly positive. Yeah? So if the equilibrium is stable, if we make this assumption, then this function u has a genuine minimum at this equilibrium configuration, and this implies that the matrix of second order partial derivatives is also positive, like the matrix T. Or another way to see it is that you say this implies that the potential must be zero, since we neglected this potential, the value of the potential energy at the equilibrium configuration. We set that equal to zero because we said it doesn't impact the dynamics. So u is zero at equilibrium, which corresponds to the vector x being zero. And u must be strictly larger than zero at all other configurations, so whenever x is different from zero. And this implies, with the same logic as for the kinetic energy, that the matrix V must also be positive. Now, with the Lagrangian in the quadratic approximation, we can write down the Euler-Lagrange equation, the equation of motion for the system. So let's recall the Lagrange function in the quadratic approximation. That was 1/2, and then I'll write it with indices, sum over I, j, tij, xi dot, xj dot, minus vij, xi, xj. The Euler-Lagrange equations read derivative with respect to time of the partial of L with respect to xi dot equals the partial of the Lagrange function with respect to xi. And this holds for all I going from 1 to f. When you insert the quadratic form of the Lagrange function, then on the left-hand side, you obtain, this is d over dt, and the partial reads sum over j, tij, xj dot. And on the right-hand side, you obtain minus the sum over j, vij, xj. You can write this in compact matrix notation. You can say on the left-hand side, well, the coefficient matrix Tij is constant. It doesn't depend on time. You can take it in front of the time derivative. And then what remains in matrix notation is matrix T applied to the acceleration vector x double dot equals, and on the right-hand side, you have minus matrix V acting on the vector x, the vector of deviations from equilibrium. Since the matrix T is symmetric and strictly positive, it's invertible, and therefore you can multiply both sides of the equation with the inverse of T, and you can write an explicit expression for the acceleration vector. This is minus, and then you have a matrix T inverse V, sort of this matrix product, acting on X. So this is a, if you write it in components, this is a system of F homogeneous linear differential equations of second order with constant coefficients. And of course, the objective now must be to find solutions to this differential equation, to this equation of motion. To this end, I would like to introduce a new kind of scalar product, which is different from the scalar product that we have used so far, that we've used, for example, to express the Lagrange function in a compact way without writing coefficients. We could express that in terms of the scalar product. I would like to introduce a different scalar product. Let's take two arbitrary vectors A and B in f-dimensional configuration space. And let me define an object A scalar product with B, and I use new symbols here. I no longer use the dot for the ordinary, as for the ordinary scalar product, but I use these brackets to denote this different kind of scalar product. And let me define that as vector A, and now the ordinary scalar product with matrix T acting on B. So T is the matrix that we had introduced in the context of the kinetic energy. And in this way, I introduce a new object, which I have yet to show that this is a scalar product. It has the mathematical properties of a scalar product. Recall that we said that T is symmetric and positive. Now, the fact that T is symmetric immediately implies that a ordinary scalar product with TB equals TA, ordinary scalar product with B, so I can take the matrix T on the other side, and the ordinary scalar product is symmetric, so this is also the same as B scalar product, ordinary scalar product with TA. And so you recognize when you look at the definition of our new scalar product that it has the property A new scalar product with B equals B new scalar product with A. So our new scalar product is also symmetric, as it should be. That's part of the fundamental properties of a scalar product. In mathematics, it has to be symmetric, and it is symmetric. Then we can look at the consequences of the fact that the matrix T is strictly positive. If the matrix T is strictly positive, then this implies that if we take an arbitrary vector A, ordinary scalar product with TA, this is 0 if and only if A is 0, and it's strictly larger than 0 otherwise. So when A is different from 0. This is, by definition of positivity, this is a consequence of the fact that, that T is positive. What's the implication of that for our new scalar product? The implication is that new scalar product of any vector with itself is always larger or equal to 0, and it is equal to 0 if and only if the vector itself is 0. And again, you recognize this is one of the fundamental properties of a scalar product, that it has this, this property. Oh, there's one thing I should mention. There are, of course, two more properties, or one more properties depending on how you count, that you require of a scalar product in mathematics, namely that it's linear in both arguments. But this you recognize immediately from the definition of the scalar product, that it's linear in both arguments. With this scalar product, we can write the kinetic energy and the potential energy in an even more compact form. The kinetic energy could be written in terms of the ordinary scalar product as 1/2 and then deviation vector ordinary scalar product with Tx. Now, using our new scalar product, we can simply write that the matrix T is incorporated in the definition of this new scalar product, and we can simply write this as 1/2 x dot new scalar product with x dot. What about the potential energy in terms of the ordinary scalar product? We wrote that as 1/2 vector x ordinary scalar product with matrix V acting on x. What we can do is that we simply insert a unit matrix in the form t minus 1 acting on V acting on x. So in terms of the new scalar product, this is 1/2 and then the new scalar product of x with T inverse V acting on x. You may wonder what we have gained by introducing this new scalar product. That's something I would like to show you on the next page. It helps in formulating the general solution of our small oscillation problem. So what's the use of this new scalar product? Let's look a bit more closely at the expression for the potential energy in terms of this new scalar product. That was x and then T minus 1 V x. In there features this matrix product T inverse V. And let's look a bit more closely at the properties of this matrix, this product of matrices. First of all, if we have a genuine equilibrium, so a unique, stable equilibrium configuration, then we had said earlier that U, the potential energy, must be larger than 0 for all x different from 0. So whenever I deviate by a non-zero distance from the equilibrium configuration, then my potential energy must be larger than 0. This implies that the new scalar product, x, and then T inverse V, x, that this must be strictly larger than 0 for all non-zero vectors x. And this implies that the matrix product T minus 1 V itself must be positive, must be a positive matrix. A second property of this product of matrices T inverse V, consider, say, the scalar product of an arbitrary vector A, and then T minus 1 V acting on B. One thing we can do is we can go back to the original ordinary scalar product, we can go back to writing this as A ordinary scalar product with VB. We know in terms that V is symmetric, the matrix V is symmetric. So in the ordinary scalar product, we can take the matrix V on the other side. We can write it in front of the A. So it's VA scalar product with B. We can insert in front of the V a unit matrix of the form T minus 1. The matrix T is also symmetric with respect to the ordinary scalar product. So the matrix T we can take back on the right-hand side in front of the vector B. So we can write that then as T minus 1 V A ordinary scalar product with T B. And this is by definition equal to, and now we write it again in terms of the new scalar product, this is T minus 1 VA new scalar product with B. What we have shown in this way is that if we take the product of matrices T minus 1V, we can shift that from the right argument of the new scalar product to the left argument of the scalar product. So what this means is that T minus 1V, this product of matrices, is self-adjoint or Hermitian with respect to the new scalar product. What this in turn implies, which I hope you're familiar with from your mathematics courses, that if you have a matrix or an operator which is Hermitian with respect to a certain given scalar product, then it's always possible to diagonalize that matrix with the help of a transformation which is orthogonal with respect to the given scalar product. So the fact that T minus 1 V is Hermitian with respect to the new scalar product implies that this matrix V, T minus 1 V, can be diagonalized via some transformation that is orthogonal with respect, again, with respect to this new scalar product. When you diagonalize the T minus 1 V, then you have on the diagonal, you have the eigenvalues of T minus 1 V. And the fact that was our first conclusion, that this matrix product T minus 1 V is positive, implies that all these eigenvalues are positive. So what we've learned is that T minus 1 V is positive and Hermitian with respect to the new scalar product. This implies it can be diagonalized via a suitable orthogonal transformation, where orthogonality is now defined not with respect to the ordinary scalar product, but with respect to this new scalar product. Associated with this product of matrices T minus 1 V are eigenvalues lambda I, which, because this product of matrices itself is positive, the eigenvalues must also all be positive, and associated eigenvectors, which I would like to call A I. So one useful consequence of, or implication of our discussion is that we can achieve this diagonalization, that we have positive eigenvalues and associated eigenvectors, and these eigenvectors form an orthonormal basis, or we can, if we take normalized eigenvectors, then they form an orthonormal basis, where again orthonormality is defined with respect to this new scalar product. So the eigenvectors AI are mutually orthogonal with respect to the new scalar product. With the help of the eigenvalues and the eigenvectors, we can write this product of matrices in the spectral representation. What is meant by the spectral representation is that you can write the matrix in question as the sum over all I, eigenvalue lambda I, times a projector onto the associated eigen vector. So AI. And I should say, when you do that, then you presuppose that the eigenvectors are normalized. So let me write this down here, that the AI can be normalized, and generally are normalized, with respect to, again, the new scalar product. If that is the case, then we have the rule that AI, new scalar product with AJ, is the Kronecker delta IJ. Let me add an extra page and make a few remarks about the spectral representation. Let's go back to the ordinary scalar product. I mean, this works with all kinds of scalar product, but for simplicity, let's go back to the ordinary scalar product. You know that any Hermitian or symmetric matrix can be diagonalized, and it has an orthonormal basis of eigenvectors and associated eigenvalues. So let's say we have a matrix A, which is positive and Hermitian. This implies it can be diagonalized. Let's say it has eigenvalues little a I and eigenvectors ei. And these eigenvectors, they form an orthonormal basis. This means that any vector x can be expanded in this eigenbasis. So for any vector x, I can find coefficients xi and write it as sum over xi times ei. When I apply the matrix A to this vector x, then this equals sum over I, xi, and then matrix A applied to the eigenvector ei, but since ei is an eigenvector, this is simply ai ei. On the previous line, how do we find the coefficients xi? The xi are the scalar product of the vector x with the eigenvector ei. So this is ei scalar product with x. Here I write it in terms of the ordinary scalar product. So on the lower line, we can also write it like this: a sum over I, ai. Then we have the xi, which we write as ei scalar product with x. and then we have EI. So formally, we can write this as sum over I, AI, EI, and then let me write it symbolically in this form, EI scalar product with X. So we can say what inside the square bracket, this is the matrix A. This is a representation of the matrix A. It's sum over I, eigenvalue AI, and then vector EI, and again, vector EI, eigenvector EI, scalar product with whatever vector this is applied to. But this is the basic idea, and this is the form that we have here on the previous page. For the spectral representation, we have this object, T inverse V, this matrix, and we write it as sum over I, then the eigenvalue, lambda I, and then the vector AI, eigenvector AI, and then again the eigenvector AI, scalar product with whatever vector this object is applied to. Yeah, so think of this whole object acting on some vector x, and then you can complete the expression in this way. Yeah, so then this has the form, the same structure as on the other page, where I just explained to you the concept of the spectral representation. And then, yeah, for the sake of compact notation, you can omit the x. So if you see that this holds for any x, then I simply erase the x and write it formally in this way. Now, also, as I mentioned on this explanation page for the spectral representation, any deviation vector x can be expanded in terms of this eigenbasis of T inverse V. So it can be written as a linear combination of the eigenvectors AI, and the coefficients are given by the scalar product of x with AI. So any vector x can be written as sum over I, scalar product of AI, eigenvector AI with x, and this is the new scalar product that we had introduced, times eigenvector AI. This coefficient in front of the eigenvector AI, this is defined as capital QI and is called the normal coordinate. And I would like to do a coordinate transformation and go from the xi that we have used so far to the capital QIs, which are the normal coordinates. So I can characterize the configuration of the system rather than with the xi. I can also characterize it with the capital QI, with the normal coordinates. This has the advantage that the Lagrange function becomes even simpler in normal coordinates. In normal coordinates, the kinetic energy T acquires the simple form, it's 1/2 sum over I, QI, capital QI dot squared. And remember the kinetic energy, that was 1/2 and then the new scalar product of x dot with itself. And now you expand x dot in terms of the eigenvectors, so QI times eigenvector AI. But the eigenvectors, they form an orthonormal basis with respect to our new scalar product. And therefore, the scalar product of x dot with itself is simply the sum over capital QI dot. squared. And remember that was 1/2 x dot new scalar product with itself. Now the eigenvectors, they are constant in time. They are not functions of time. Only the coefficients, the normal coordinates, are functions of time. So we have 1/2 sum over ij. Now the first x dot argument, that is sum over I qi dot ai. So we have a qi dot ai. The second, the right argument, x dot, that's sum over j qj dot aj. So that's qj dot aj. Now this is an orthonormal basis, so this is the Kronecker delta. And what remains is the sum that I had written before. So in terms of the normal coordinates, the kinetic energy becomes very simple. We can do the same for the potential energy, and the formula for the potential energy in terms of the normal coordinates also becomes very simple. Remember, the potential energy in terms of the new scalar product was given by 1/2 x new scalar product with T inverse V applied to x. Again, we use the expansion of x in terms of the eigenbasis. So then we have 1/2 sum over ij. The first x we expand as qi, and then we have an ai. Here in the left argument, and the second x we also expand, and then we get a qj and an aj. Since aj is an eigenvector, this is simply lambda j, aj. Since this is an orthonormal basis with respect to the new scalar product, the scalar product of ai with aj is a Kronecker delta, delta ij. So one of the two sums collapses. We are left with only one sum over I, and then we have lambda I qi squared. So it's a simple expression for the kinetic, for the potential energy too. Taken together, we can formulate the Lagrange function L as a function of our normal coordinates, capital Q and capital Q dot. This is 1/2 sum over I. I take this in front, and then we have kinetic energy, which is simply qi dot squared, minus potential energy, which gives a lambda I qi squared. This Lagrange function gives us the equation of motion for the normal coordinates via the Euler-Lagrange equation. The Euler-Lagrange equations for the normal coordinates are qi double dot plus lambda I qi is equal to 0. And we have this for all I going from 1 to f. And you recognize for any given I, this is the equation of motion for a harmonic oscillator. So we have f independent equations that all have the form of a harmonic oscillator equation. So we have f decoupled, independent decoupled harmonic oscillators. And each of these decoupled harmonic oscillators is a one-dimensional oscillator with respective frequencies. Well, when you have a harmonic oscillator equation, then in front of the qi you have the omega squared, where omega is the frequency. So we identify the frequency with the square root of lambda I. And this is well defined because we said earlier the eigenvalues are all positive. So the square root has a real value. And so the frequencies are real, as you expect for a physical harmonic oscillator. Now, what are the solutions? Or what is the solution of the harmonic oscillator Qi of t? When we have a harmonic oscillator with frequency omega I, then the solution is some constant Bi, arbitrary integration constant, times the cosine of omega I times t, plus some phase, that's also an integration constant, an arbitrary phase, alpha I. This is the solution assuming, as we have done all the time, that the frequencies are strictly larger than 0, so the eigenvalues, lambda I, are strictly larger than 0, and therefore the frequencies are, omega I, are strictly larger than 0, and then you get this form for the solution with the b and the lambda as integration constants. You can generalize the whole discussion that we have made so far and include the case where the equilibrium is not a unique minimum, but you allow that one or several of the eigenvalues of this matrix T inverse V can also be equal to 0. It can never be negative, can never be smaller than 0, because then this clearly would not be an equilibrium, but you can generalize and allow for eigenvalues that are equal to 0, and I will show you in the example this will actually be the case, and I will explain to you what the physical meaning of that scenario is when one or several of the eigenvalues are equal to 0. So if you allow that, at least formally at this point, that an eigenvalue may also be equal to 0, and therefore the frequency might also be equal to 0. In that case, the equation of motion would simply be Qi double dot is equal to 0, so no acceleration at all, and the solution for that equation of motion is a uniform motion. So in that case, the solution would be AI plus BI times T, a uniform motion where now AI and BI are integration constants, and that is for eigenvalue equal to 0. To summarize, what we have done is, starting from the basic setup for small oscillations, we have done successive coordinate transformations. First we did the quadratic approximation. We went from original coordinates little qi to xi, which are the deviations from the equilibrium configuration. And then we made another coordinate transformation. We went from the xi to the capital Qi, to the normal coordinates. And these have the advantage that the Lagrange function becomes extremely simple, and the equations of motion for the capital Qi's, for the normal coordinates, are simply F decoupled harmonic oscillators. And then we can immediately write down the solution.